up guys, and welcome back to my channel. Today in this video we're going to be interviewing Dr. Cécile Caillol, who is an amazing and inspirational physicist who works at CERN laboratory, which is located in between France and Switzerland. And so we're going to be actually learning her point of view and what she studies in her field in physics, such as particles, which include the Higgs Boson, the Standard Model, and much more. So today, we're going to be interviewing Dr. Cécile Caillol, a female scientist, and we're going to be seeing her point of view on it. Let's go.
So it's a very big collaboration with people from many different countries. We have like very big communities in the United States, also big communities in China, in India, in Europe. The CMS detector is one of the detectors at the LHC. So the LHC, it means Large Hadron Collider. It's a collider of protons, so it makes collisions between two protons at a very, very high energy. In particle physics, we use the Standard Model to describe the interactions between particles. So there are some interactions that are possible, some are not.
So here guys, we're with the woman herself, Dr. Caillol, and we're actually going to be talking about her view and her perspective in the world of physics. So, first of all, welcome to the show, Dr. Caillol.
Thank you.
Hello. Thank you so much for being here. And so, yeah, let's just first of all ask some questions to know you better, and then we can start off explaining more about your field. So, first of all, what inspired you to become a physicist?
So I always liked science, like since I was a child. Like my grandmother always said when I grow up, I would be a scientist, and she was right. So I was always interested in science, and also I liked mathematics at school. So at school, what I preferred was math clearly from beginning. And then after, even still in high school, I liked math a lot, and I ended up studying engineering. And then in engineering, I had physics classes. And I really liked the physics part because you get to understand things in nature. And what actually these physics laws are very beautiful. So what I liked is that the beauty of the physics is very logical, and it's great to see that this logic in nature. And then that's how in the end I didn't stop engineering, but I didn't continue as an engineer, but I became a physicist because I really like this beauty.
Okay, so you started off strong as a kid, liking science and aspiring to become a scientist, and then eventually you were right and you became a scientist, and then you were studying engineering, but then eventually you were in engineering, you were also doing some physics, then you got inspired by that. Amazing. Okay. And so I just had, by pure curiosity, what are you in terms of physicist? Like you were saying, you have many types of things that you can do as a physicist. Just by pure curiosity, what do you do as a physicist?
So I'm mostly work on physics analysis. So I look at the data we have collected, and then I look for a particular signature. For example, these two tau leptons. So I look in the data whether we see tau leptons. And then there's also a big component of statistics. Like you see some like 100 events, you expect that you would have seen 90. Is it compatible? Is it not compatible with the Standard Model? So there's a big part. So the first part consists in the analysis of data. So for this, there's a lot of coding. You need physics because you want to design the analysis to really follow the physics principles. And then after that, you have a lot of statistics where you try to analyze your data to understand whether you have seen new physics, whether it's compatible with our expectations. So there's also a lot of statistics. So that's what I work on most.
Interesting. So now let's talk a bit more about, more about your field. So first of all, what is a CMS detector and what exactly does it see?
So the CMS detector is one of the detectors at the LHC. So the LHC, it means Large Hadron Collider. It's a collider of protons. So it makes collisions between two protons at a very, very high energy. So the protons circulate in the LHC at about the speed of light, and then they collide together. So the LHC, it's very big. It's 27 kilometers. And so the protons collide in a few points, and at each of these colliding points, there is a detector. And so the CMS detector is at one of these interaction points. So the protons, they go very fast. And when they go very fast, it means they have a lot of energy. And when you have a lot of energy, you can convert the energy to a mass because energy and mass is about the same thing. And so when you collide the protons, you can create particles that are very heavy. And then these heavy particles, in general, they're not stable. So stable particles is, for example, the electron, also the photon. So there are very few stable particles. But when you collide the protons in the LHC, they produce very heavy particles which are not stable and will decay immediately to other particles. And what we do with CMS is to actually record these decay particles, so the decay products of the heavy particle. And so the CMS detector, it's like a camera, which is taking pictures very, very
Yeah.
often. And these pictures, we see the signature of the particles in the detector. So when there's a particle that crosses the detector, you can detect it with different kinds of technologies because they will, when they go through some material, they can leave like energy deposits. And that's what we see. So we just see the path of the particles that crossed our detector. And these particles, they are the decay products of other particles that we manage to produce when we collide the protons.
Nice. Okay. And so what are tau leptons? And uh but like how can you find them? Like what are they? And also why are they so hard to detect?
Yeah. So you know about the electron, right?
Yeah.
And do you know about the muon?
I'm not aware of that. I
Okay.
mean,
So the muon is another, so the electron, it's a lepton. It's a family of particles.
okay.
And so the electron has some heavier cousins. So a bit heavier is the muon. So it's also a lepton, which means it has kind of the same properties, like it also has an electric charge like the electron, but it's heavier. And then there's a even heavier cousin, which is the tau lepton. So the tau lepton is much, much heavier than the electron, and it's not, it's going to decay. So the electron, you can see it in the detector. The muon also, so the muon has still, is going to, so it has some, it's going to cross the detector. You can detect a muon because in the detector, we have muon chambers. So the muon chambers will help us to detect the muons. But for the taus, immediately after they are produced, they are going to decay. So you can never reconstruct a tau itself. You will see only its decay products. And it can decay in different ways. So it's not always the same way. So it can decay to an electron plus some invisible particles that just escape our detector. It can also decay
Okay.
to a muon plus the invisible particles, or there's also another way to decay. So there are many possible signatures for a tau. So it's harder than an electron to detect because there are all these possibilities. And
Oh,
yeah.
okay. And so how does it actually decay?
So it decays immediately to particles, and there are several kinds of interactions that are allowed. So in particle physics, we use the standard model to describe the
Yeah.
interactions between particles. So there are some interactions that are possible, some are not. So for example, you need to conserve the electric charge. So if you
Mhm.
have a particle which has a electric charge of +1, it can decay to a sum of particles, but the sum of the particles should also have electric charge +1. So there are some rules that we always must follow for the
Sure.
decays of the particles. And for the tau, there are different possible decay modes in our theory, and we know the probabilities for all of these decay modes. So that's something we can calculate, and we have also measured with other experiments in the past. So we know the possible decay modes, we know how they look like. The problem is just that it's a bit difficult to really look for each of these possible decay modes. And also the problem is when we have tau leptons, in their decay mode, there's always at least one neutrino. Do you know the neutrinos?
Yeah.
Yeah. So the neutrinos, they interact only weakly. So when they cross the detector, we don't see them at all. So the taus always have an invisible part that we cannot see in our detector. And that makes them also more difficult to detect compared to electrons and muons that are completely visible in our detector. We can measure their energy precisely. For the tau, we will never measure their energy precisely because there's always at least one neutrino that we just don't see.
Okay, amazing. And so, can you explain how scientists actually see a Higgs boson decay in a tau lepton?
Yeah, so the Higgs boson is produced in a collision with a proton. So the Higgs boson is a very, very massive particle. It's much, much heavier than an electron. It's also much heavier than a tau, which is the heaviest of the leptons. So it's a particle that is very massive. That's why we couldn't produce it in the past. So there have been other colliders, not at CERN or also at CERN, and it couldn't be produced. So we really needed the energy of the LHC to be able to produce the Higgs boson. So the Higgs boson, when it's produced, it's going to decay immediately. And it has
Mm.
also different decay modes that are possible. And one of them is the tau lepton. So the Higgs boson is really related to the mass in the Start model. And the tau lepton, I told you, is the heaviest of the leptons. So in the Higgs boson, it's not going to decay to electrons, almost never, but it's going to decay to the heavy particles. So it's going to decay to tau leptons. And
Oh, okay.
basically in the detector, what we will see is just so when the Higgs boson is produced, then it's going to decay to two taus, which are basically back to back. And then we are looking in the detector whether we see energy deposits that are compatible with tau leptons back to back. So we are going to analyze a lot of events and
Oh,
then
okay.
check how the detector looks like the signature in the detector looks like. And then we can see whether it's compatible
Yeah,
with what we would expect, thanks to the Start model, what we would expect for Higgs boson decaying to two tau leptons.
sure. Okay, thank you. So you're saying that the Higgs boson is another very heavy particle which occurs from a collision,
Mhm,
and you're saying that as the Higgs boson starts to decay, because it decays very fast, like you say,
mhm.
um, I think I was researching about it. I believe it was like a trillionth of a second or
Could
something.
be. Yeah, I don't
Okay,
know the exact.
all
Yeah.
right. And so since it decays so fast, it decays into multiple steps, which you're saying first decays into tau leptons. I believe you said like three tau leptons or something.
Two tau
Oh,
leptons.
two, yeah.
Yeah,
So then it
back.
decays into two tau leptons, and then rarely decays those two tau leptons into into electrons. Sorry.
Yeah, so the tau leptons can decay
Yeah,
to electrons and neutrinos then
and
also. But
neutrinos. Yeah.
the Higgs boson itself is not going to decay to two electrons. It's very, very, very rare. So it basically, we never saw that.
So the Higgs boson is very rare to decay on into an
Yeah,
electron. Okay.
yes.
But you have seen it, but it's very rare.
No, we have not even seen it. The Higgs boson
Oh,
decaying
okay.
electrons, we have not seen it because it happens so not
Fast.
frequently that it's just not frequent at all. So it didn't happen in our collisions and we couldn't see
Are
it.
you aware of why it might appear sometimes or why it might not?
So it's all related to the Start model in our law. So the probability for it to couple to the particles for the Higgs boson, it depends on the mass. And the electron is very, very light, so the probability is very, very small. For the tau is very
Oh.
heavy, so the probability is much bigger. So it's the Higgs boson is the particle that is related to the mass.
Oh, sure. So you have to look for the actual good weight for the Higgs boson to then make sure it actually transforms to an electron. That's why you don't haven't seen it yet because you still haven't figured out the exact weight needed.
It it just the Higgs boson doesn't like the probability for the Higgs boson to decay to electrons is so small. So it
Yeah.
doesn't depend. So the Higgs boson has some mass, and also it's just the total probability is 100%. But then if there are heavier particles, they will always be preferred. So the probability to decay to electrons is just small, and we cannot do anything about it.
Oh yeah, of course. So scientists are still working on the standard model to
Yeah.
then try to implement the probability
Mm,
into an actual formula and understand it a bit
yes.
better. Okay,
Yes.
amazing.
But if we had seen Higgs boson decaying to electrons, that would be new physics because we don't expect to see it. So if we see it, we would be very happy because we would have discovered new physics. But now we have not seen it, which is what we expect.
So, just one thing to sum up, from what I understand is that a standard model is like a blueprint, which basically tells you how particles like quarks or other particles, whenever they collide and interact with different other particles, the standard model basically tells you how they can react with each other depending on the actual fundamental rules of
Mhm,
nature.
indeed, yeah.
Yeah, okay, physics. Great. Okay, so my next question. What does it mean to look for new physics beyond the standard model? And can you give an example of that?
Yeah. So the standard model, so as you explained, so it's our theory to explain how the particles interact with each other. And the start model is very, very, very successful. So it's incredibly successful because we can, like all the measurements we are doing at CERN, so all the time we confirm the start model. So the start model is really powerful to describe the physics around us, and also so it can predict, so it really makes predictions that we can check. But we know there is physics beyond the start model. So, for example, you have heard probably of dark matter.
Yeah,
So
of course.
the start model can describe the visible matter. It cannot. We know there is dark matter, but dark matter is not part of the start model. So that's really we don't know what dark matter is. We don't know, for example, if particles constitute the dark matter. And we would like to have a theory that can also explain the rest of the universe. We need to explain dark matter. We also need to explain dark energy. And at the moment, the start model cannot do it. So we know there is physics beyond the start model. So we are searching for it.
Yeah. Okay, sure. So are we getting closer? Would you say like are we getting closer to discovering new particles? And what are some like the big mysteries physicists are still trying to solve? Because you've been saying that one of the mysteries are of course the Higgs boson turning into electron. That's a big mystery, I assume, I suppose. And so can you tell us other big mysteries that physics are still trying to solve? And are we close to discovering any new particles?
So the mystery, so I would say dark matter is clearly one of the big mysteries because we know there is dark matter. We also know there's dark energy, but especially dark matter, and we cannot explain it with the start model. So that's really one of the big mysteries. There are also other mysteries. For example, so at the time of the Big Bang, there should have been the same amount of matter and antimatter. But now in the world we live in, we can clearly see there's matter. And so at some point, there must have been some asymmetry between matter and antimatter that in the end, we are left with more matter than antimatter. And this also the start model cannot explain why. So that's one of the other big mysteries. But there are also others, so the all other kinds. And so we know there is physics beyond the start model. And as you said, we are looking for it. I don't know if we are getting closer because the problem is we don't really know what we are looking for. We don't have a prediction of what the new well,
Yeah,
or we have thousands of predictions of what the new particles could be,
sure.
but we don't have a single hint. Like, I mean, when we were looking for the Higgs boson, we were looking for something in particular. Then we found it in 2012, but we had really been looking for the Higgs boson. And now there are many, many new particles that we could find, but we don't have a strong bias towards which one is the favorite one. So
Hmm.
we are really looking everywhere,
Okay.
and maybe we are getting closer because we are searching more and more. We are searching in very special signatures. So maybe we are getting closer to new physics, but we cannot estimate when we'll find new
Okay.
particles. Yeah.
So the end goal of physics, that what you're saying is that we're able to understand most of our universe and put it all into a standard model.
Mhm. Yeah. So we really what we are trying to do now is to find a bigger theory compared to the start model that could explain even more. So the start model is successful at its energy scale, but we know there is more, and we are really looking for that, and that's what we
Of
are
course.
really
Okay.
doing at CERN.
And so what do you think is the most exciting or surprising thing that you've seen in the data and testing so far?
So I would say the discovering the Higgs boson was really a very big time for the LHC. So the Higgs boson was discovered so in 2012, and that was really, really an exciting time at CERN. So everybody was very excited. It was discovering a new particle. It was really the last missing part of the start model. So in the start model, we needed the Higgs boson to explain the origin of masses. And so discovering it was really confirming the start model was working well, and that was really exciting to see in the data. And then
Oh,
since
okay.
then, we have not discovered new particles. We are looking for them, so I hope we will find some. But yeah, that was exciting.
Okay, amazing. So can you just quickly explain, because from what I understand is that Higgs boson, from what I understand from your explanation, is that the Higgs boson is just a heavier particle than the tau lepton. But can you explain a bit more, what makes this Higgs boson so particular and how can this actually help us understand mass?
Yeah, so it's true. So it's heavier, but it has completely different natures compared to the other particles. Like I told you, so in the leptons, we have the electron, the muon, the tau. These have an electric charge, The Higgs boson is neutral, so it's a different kind of particle. We also have other, so the charge is one of the attributes of the particles. We have also other kinds of attributes, and the Higgs boson is unique. So there is no other particle in the CERN model that is similar to the Higgs boson. And so it was postulated to exist in the CERN model. So you need to have it in the equations to be able to explain things like the mass of the particles. So without the Higgs boson, you cannot explain how particles have a mass. So it
Yeah,
was postulated based on the formula. So mathematically, we needed it to make it work. And then that's what is impressive actually, because we thought it would exist just based on mathematics. And then we built this experiment and we saw it where we predicted it thanks to the formula. And that's quite impressive, I think.
sure. Okay, okay. So I just had a one question. So, what is the true nature of the Higgs boson? Because you're currently saying that it helps us. I understood your definition. I was just wondering a bit more on more of the true nature, which made it more like special in a way.
So in the start model, it's scalar particle. So it's another elementary particle.
Of course.
And I don't know exactly what else to say. It's just because of its scalar nature, it works in some way in our equations. It has some kinds of couplings that are the ones that are needed to explain the
Oh,
existence
sure,
of the
sure. I
mass.
get it.
But it's a bit technical actually, and
I
so I don't know
understand.
how to.
No problem. Okay, okay. And so, how many people work with you at the SMS experience? I mean, yeah, SMS
CMS.
experiment. And is it like a giant global team, or how does it work?
Yeah, so for in the CMS collaboration, there are more than 4,000 people working for a CMS collaboration. So it's really huge. Yeah. So it's a very big collaboration with people from many different countries. We have like very big communities in the United States, also big communities in China, in India, in Europe. We don't have a lot of African countries at the moment, but there are always new countries joining. And
Yeah,
so there are people who are based at CERN, like I'm based at CERN, but there are also people working in their home country, and we all have meetings together on Zoom, and sometimes we also have collaboration weeks. So like 1 week per year, everybody tries to come to CERN, and we can meet at that moment. But most of the time, we are just having meetings with everyone from all around the world connecting on Zoom.
I mean, seems fun. All right. Okay. Okay. And so, if you can discover a new particle tomorrow, what would it be?
I would say any particle. I would be happy with any particle, any elementary particle, because any elementary particle would be a huge step in our understanding of physics. So it would really open a new discipline. Like we would have to understand what it is, how it fits with the standard model. Any new particle would be amazing.
Any. Okay. How do you think AI will impact the future of physics, especially in your field?
Yeah, we are already using a lot of AI. So we started already years ago, and now it's playing an even bigger role. So it's a very um, logical place to use AI because we have a lot of data that we collect. So we have a lot of data to train, and we have a lot of data to check. So it's easy for us to collect data that we can use to train our AI models. And so we use it a lot to tag particles. So tag, for example, I told you that tau are not very easy to detect. It's a
Yeah.
bit tricky, the signature they leave in the detector. And we are really improving our efficiency to tagging the tau using AI. So that's something we are already doing now. Now, also what we are trying to move towards is the anomaly detection. I don't know if you have heard of anomaly detection. So it's basically also a AI way to look for events that would behave differently from the others. So we record a huge quantity of events, and when we analyze by ourselves, we are always biased. We are looking for some particular model, and that's very efficient for this particular model. But there are many other ways that we have not predicted. And so with anomaly detection, the AI is going to look for events that just look different from the others. So it manages to find events that are different, and
Oh,
then we could analyze these events, and to maybe it will be the way we find new physics in the end by these anomaly detection techniques, where we will really be able to to single out the events that look different. And so that's really a new avenue that we are looking into to find new physics.
Amazing. Thanks so much. Okay. And so, what advice would you give to kids who would dream to become a physicist like you, of course? And what would be your message to them who would want to, well, work at CERN?
Yeah, I think they should. So if they like it, they should just trust themselves. I don't know if you can say that, but they should just be confident. Like if there are many ways to go to CERN, so you don't all need, or you should figure out what you like, what you are good at, and there are many different skills that are needed at CERN. So you can be a physicist, but even in a physicist, you have different kinds of physicists. You
Skill.
have those who work more on hardware, those who work more on the formulas. Then you have engineers. Then you have also people working on the law side. So there are many actually many different ways to go to
Mm.
CERN. There's not a single profile. Like everybody is welcome. You just need to figure out what you like, what you are good at. And also there are many opportunities like to see if you like it. There are many, so CERN is doing a lot of outreach. There are master classes online that you can join. You can ask your professors to check what the opportunities are. Even we have opportunities for primary school, high school. We have virtual visits. You
Yeah.
can already start with a virtual visit, so just on your computer. So just see and just believe in your own skills. And we need very different profiles. So you don't need
Oh
to be
my God.
the best in your class at mathematics. If you like what you are doing,
Oh,
it's good enough.
well, thank you so much for today's amazing interview,
Thank
Dr.
you.
Caillol. And yeah, so thank you so much for being here.
Thank
This
you.
was very useful. And yeah, thank you.
Thank you.